Back with the mean value theorem and an explicit example. We have a given function on a given interval. Here it's x cubed plus x minus 1 on 0 to 2. And there's two tasks. One is to verify that the hypotheses of mean value theorem are true here, and that therefore we can expect that the conclusion is going to be true. That we're going to find some particular magic c that gives us an appropriate tangent slope. And then the second part is a little bit weird because it says, well, what if we didn't believe MVT? What if we didn't really trust this whole theorem? What if we actually wanted to find them for ourselves, like we usually do, explicitly? How could we do that? As I said with Rolle's theorem, the real value of MVT is when we can't do this second part. If the algebra is too hard to do this, we still want to know that they're out there, even if we can't find them explicitly. But let's do this. This is actually slightly easier than with the Rolle's theorem problems, because there's one fewer hypothesis. In Rolle's theorem, it had to be continuous on the closed interval, differentiable on the open interval, and it had to have the same value. F of A has to be equal to F of B. That wasn't hard to check. But in MVT, that's not required. This is like Rolle's theorem, but it's kind of a tilted version, that these two endpoints don't have to be the same. Don't have to be at the same height. So, all we do is we just say, look, F is a polynomial. Therefore, it's continuous and differentiable everywhere. End of story. Now, where we'd have to be skeptical is things like square roots, 1 over x, ln, tangent, cotangent, anything that has a discontinuity or a point of non-differentiability. Trickiest ones are probably going to be absolute value, because those are continuous, but they're not differentiable, and you do have to watch out for those. But here, it's continuous and differentiable everywhere. So that's it. We're done. The hypotheses are satisfied. So let's see what MVT says. MVT really is a two-step process. It says calculate the secant slope over the whole interval, the average rate of change over the whole interval. And then it tells you what the magic number is, what the magic slope is. Before that, you don't even know what the theorem is even going to guarantee you. So the overall or average or secant slope is just f of b, minus f of a over b minus a. So that's divided by 2, because that's the length of the interval. F of 2 is 8 plus 2 minus 1 is 9. F of 0 is 0 plus 0 minus 1, that's minus 1. So that's 10 over 2 is 5. And so what we're doing is MVT claims that this function, if we look at the derivative, that there will be a solution to this equation, and not only some solution, it should be some x, so it should have a solution for some x in the interval. It wasn't that there's some totally unrelated x that had the right slope. There should be some x in the interval where that actually works. And so we just move the 1 over, and so x equals 2 over root 3, or if you like to rationalize, it's not a big deal. 2 root 3 over 3. Well, let's see. Is this actually between 0 and 2? It's certainly positive, and it's less than 2 because I'm taking 2 and I divide by root 3, and root 3 is bigger than 1. Okay, so yes, you do want to check this. And what you might have sometimes is you'll solve this equation, and you're going to get more than 1. In fact, I kind of fudged that here. There's really a plus or minus. Okay. And so really we only wanted the plus one. So that's a tricky thing about these problems, is you're going to get maybe 2 places where the slope is the magic value. But the other one is not of interest to us because it's not in our interval. So if you actually look at what the graph of this thing looks like on 0 to 2, you can use your calculator to check this if you want. It starts out minus 1, goes up to 9, and roughly looks like this. Okay. Here's the dotted line, and somewhere in between is that tangent slope. And we found exactly 1 point here in the interval. Now there's some other point way over here. It maybe looks like this or something. There's some point outside the interval that had that same slope that was parallel, but that wasn't of interest to us in the problem. So that's a prototype for a simple mean value theorem problem. And we'll do ones that are a little bit more interesting, where we were a little bit cleverer about the use of the theorem, but we'll save those for later.